Give me one moment and we'll be underway. Okay, do we have sound? Okay, I think so. Okay, so you might know me from the Ubuntu and Debian packages that I provide for Phoenix. I'm a Debian developer, so I also provide other packages, PETC, SciPy, among others. But the reason I provide these packages is because I use them for my own research. And that's what I want to talk about today, in particular, some aspects well, some tricks that I use to manage the nonlinearity in the system. So first, I'll acknowledge some of the co-workers and funding providers, and in particular, I want to highlight Dagmari Tades, who's recently graduated, completed his PhD in Australia. He's the one who got this modeling going forward with me. Aline Gregoris from the University of Calgary, who helped convert from Dolphin to Dolphin X, important step. And Matteo Facci, who's currently working on these ideas. So what I actually do is physical chemistry. I'm interested in the interaction between particles in solution, absorption of electrolyte of ions in solution to surfaces, and there's a whole bundle of reasons why this is interesting. Electrolytes are everywhere in physiology, in industry, in chemical processing, mineral processing, in marine applications. So the broad perspective we bring in is the idea of ions in solution, the absorption, a counter ion will absorb to a charged surface. The electric field is built up, and that has implications for the energy, the forces between particles. Fundamentally, we need to describe the thermodynamic potential of the system. I've identified the key parts. Don't want to spend too much time on it, but I'll draw attention to the three main steps. Let's call it three, of which I have two here. So there's the electrostatic energy, the energy of the electric field itself, which is associated with the energy of the charges interacting with the electrostatic potential. Second term is subtle but important. That's the ideal energy of particles, treated as an ideal gas. They're the ions, according to their concentration profiles. And there's a ... below the line, van der Waals energy, indicating there are other things for the actual system. We may be aware of other interactions that we need to describe the actual system. But in terms of the basics, we have the electrostatic potential, we have the concentration profile, and that's what we need to get things started. One small but kind of important point is the C0 here. That indicates the bulk concentration. So this model, we're assuming that we have that the system is exposed to an infinite reservoir of bulk concentration, providing ions. And a point for the thermodynamics, that means we're dealing with the grand potential, not the free energy. So you'll sometimes see the energy functional described as free energy, but if there's a bulk concentration, then it's a grand potential, not a free energy. You'll see that there's no differential equation yet. So fundamentally, the strong formulation is beside the point, but we can get there by variational principle, minimizing this the energy functional, which also leads to the weak formulation. So we can get to the, we don't need the differential equation, but if you want to see it, this is what it looks like. So we have the Poisson equation associated with the electrostatic energy, and we have a Boltzmann equation associated with the entropy of the ions, and those two together make the Poisson-Boltzmann model. So that's what we're solving. So what are the things to consider? Firstly, if we're talking about normal surfaces in normal electrolyte solutions, then the magnitude of the electrostatic potential we're dealing with is somewhere like 10 to 50 millivolts. That's the potential of protein molecules, the potential of mineral oxide surfaces. But if we measure that in terms of thermal energy relative to temperature, kT, that's around 1 to 4 kT. That's the normal energy of normal surfaces. But in electrochemical applications, obviously a normal battery is how many volts? 9 volts, 12 volts, 1 volt, that's 1,000 millivolts. So when we're dealing with electrodes in electrochemical contexts, in terms of thermal energy, we're dealing with the energies of 40 to 200 kT. And that's where the numerical computations start to become more challenging. So to take a picture, what we have here is, on the left is the solution to the electrostatic potential shown on a log scale on the left, and the counterion concentration on the right. So we can see on the log scale, we have a linear plot indicating that we could use linear approximations up to about, let's say, 100 millivolts. So that's about 4 kT. But when we get above that 400 millivolts, we can see the non-linearity starts to become more apparent. And more to the point, if you think about the Boltzmann factor, 10 to the power of 2 kT, that's getting somewhere around 10, now in chemical units, moles per liter. And that's already getting to saturation concentrations. So once we're in electrochemical systems of 1 volt, that means a Boltzmann factor is 10 to the power of, it's off the scale, 8, which is obviously unphysical. So there's some things we need to think about to manage modeling of electrochemical systems. So there's 2 challenges that we need to deal with. First, we want in terms of running the calculations, we want a consistent convergence criteria. So you don't want to be tweaking the parameters each time we change to a different electrode potential. And the other thing is we need the solution. We need to get a convergence. So there's 2 techniques which I'm using to manage that problem. The first is, well, not so strange, scaling of the function. But the one thing which is maybe a bit more novel is the throttling. I have a throttling algorithm which I'm presenting today. So first, scaling. The simplest way of scaling is just getting a non-dimensional by, let's say, in terms of the concentration, we divide by the bulk concentration, or possibly divide by the Boltzmann factor, the concentration of the counterion. That gives some improvement. We can get up to 400 millivolts. But above that, there's an issue I'll show. Now, it's traditional to show some Phoenix code, so here it is. You can activate the log level. So in Phoenix X, it's been deactivated, but we can switch it on and see the details of what's happening in the nonlinear solver, the Newton solver. So for this one, we're calculating, I think this is for 1,000 millivolts. So we can see the residuals start high, get low, 10 to the minus 5, but not quite. So we're stuck around 5 times 10 to the minus 5. That's one challenge. So obviously we can consider it converged by the time it gets here. We can set the convergence criteria, but when we start playing that game, that means we have to fiddle with the tolerances for each calculation, and that's not really efficient. So a better way is to consider scaling the function itself. And given the form of the concentration, roughly speaking, exponential with respect to the potential, so the obvious approach is to take a log function, log scaling. One thing that I was concerned about is for the co-ion, that's the ion with the same charge as the surface, the concentration gets depleted down towards 0. So I was concerned that log scaling might end up with values of towards minus infinity for the co-ion. So log scaling is okay for the counterion. But for the co-ion, to deal with that, I invented this more complicated scaling function. So it's, we have the log scaling, but I've shifted it by a +1 so that the value for the co-ion remains above 0 without falling to minus infinity. And to compensate for that, they've subtracted off a log2, which is the value in the bulk solution. So the scaled function goes to 0 in the bulk function, the same way that the electrostatic potential does. There's another scaling factor, again, for the co-ion to keep it contained between 0 and 1. So I thought that was a clever way of doing it, but when we can extract back the physical concentration by inverting, of course. And so to me, it seemed like a clever idea, but actually when I stopped to have a closer look, it performs the same as the simple log scaling, but not worse. How are we going for time? I should speed up a little. Ultimately, the reason for the nonlinear catastrophe is physical. The model is incomplete. So what's missing is the finite size of the ions. So there's a little bit more of thermodynamics, another term in the total grand potential, the energy functional, which we can add. And when we do, so that brings us to the other problem. When I introduce that term, it's a bit like what Pavan said yesterday about using log functions. So when you put a 0 into a log function, you get infinity. So that's the next problem for doing the calculation. So this is where throttling comes in. We know in the safe linear regime, we can obtain a solution, and that's the step. So if we're in the region of high potential where we have these nonlinearities, the approach is to throttle the boundary condition down to a safe value where we can obtain a solution, and then use that found solution as the initial guess for the next iteration, and then raise the boundary condition back up again. So the process, we need to find a balance between applying the throttle and lifting it back up fast enough. So we want to get the solution as fast as possible. So this kind of works. If we have a failing solution, we apply the throttle by reducing the boundary condition by 3/4. If we get a solution, we can increase up by 1/4 and keep iterating until the throttle gets back to 100%, and at which point we have the solution. And we can stop. And so when we do that, we find we can get solution of, well, 1 volt. So getting to electrochemical applications becomes accessible. This is the effect of the finite size. It's quite a big difference from the naive model of the electrolyte. And in fact, we can push that up using that algorithm up to 4 volts. So we can start to deal with battery applications or electrochemical applications. 4 volts is the limit using the algorithm at steps of 25. If we reduce it further to a step of 10% rising rather than 25% rising, then we can get to 20 volts. If we take it more slowly and move the throttle up in 5% steps, then we can get to 100 volts. So we can start studying electrocution in Japanese and American bars. Unfortunately, we can't get to 240 volts. So if you have further ideas of how to develop this to get to 240 and above, that would be interesting. So to wrap up, what Matteo is doing is applying it, comparing it to cyclic voltammetry, and we say, well, the technical detail, we get this level of agreement of the experiment. So I think we're on the right track. It's an illustration of interesting things that we can do with the application. We can get peaks in the cyclic voltammetry, in this case, pH dependent, but it's time to finish. So what do we have? On the physical side, we need to add the finite size of the ions to get the proper match with experiment. On the computational side, we need to scale the function. Log scaling seems to work well enough. But throttling is, I guess, the main idea which I'm presenting to you. We can get extreme boundary conditions working if we apply this sort of algorithm. Thank you.
We'll take questions after. I'm going to write over to you.